We've already uncovered two main ways that binary numbers can be represented. Firstly, the unsigned representation. This is the simplest form of binary that we're all pretty familiar with by now. The values in unsigned representation are always positive, because we're not designating any of the bits to represent a sign. Secondly, we've encountered the sign and magnitude representation. This method allows us to represent both positive and negative numbers. We accomplish this by using one bit, usually the leftmost one, to indicate the sign, 0 for positive and 1 for negative. But our binary journey doesn't end there. Computer systems use even more sophisticated methods to represent numbers in binary format. These additional methods, like 1's complement and 2's complement, allow for a wider range of numerical expressions and computational efficiencies. We're going to dive into these representations and shed light on their importance next. As we delve deeper into binary number representations, let's now explore a unique and intriguing form known as 1's complement. This approach takes a binary number and inverts all the bits, meaning that every 0 is replaced with a 1, and every 1 is replaced with a 0. For example, consider the number 7. In binary, using an 8-bit representation, this positive number looks like 000000111. In the 1's complement system, positive numbers are represented exactly the same way as in the unsigned representation. So, 7 remains 0000111. However, to represent a negative number in 1's complement, we flip the bits of its positive representation. Thus, to represent -7, we take the binary for 7 and invert all the bits. This turns 000000111 into 1111100. To better understand and get comfortable with 1's complement, we're going to work through a few examples in our upcoming discussions. It's another important step in demystifying the complex yet fascinating world of binary numbers. Let's take a deep dive into our first example of using 1's complement representation. We'll start with a simple task, converting the decimal number 9 into binary. When we deal with positive numbers in the 1's complement system, we follow the same process as for the unsigned representation. So, since 9 is a positive number, our task is pretty straightforward. We begin by translating 9 directly into its binary equivalent. If we're dealing with 1 byte or 8 bits, we have 8 places to fill, turning on the bits that correspond to the powers of 2 that add up to our number. So our 1's complement binary representation for the number 9 looks like this: 0001001. As you can see, representing positive numbers using 1's complement is as simple as using the unsigned binary representation. This is the foundation upon which we'll build as we dive into more complex examples involving negative numbers. Let's move on to another example, this time involving a negative number. Our task is to represent the decimal number -12 in binary using 1's complement. Now, when dealing with negative numbers in the 1's complement system, there's an additional step compared to positive numbers. Here's the process. First, we're going to ignore the negative sign and just focus on the magnitude of the number, which is 12. We convert this number to its unsigned binary representation, just like we did with positive numbers. Remember, 1 byte has 8 bits, so we have 8 places to fill. Converting the decimal number 12 into binary gives us 000001100, which is the binary representation of 12 in unsigned format. Now comes the unique step for negative numbers in 1's complement. We need to invert or flip all the bits. Every 0 becomes a 1, and every 1 becomes a 0. So if we take our binary number 000001100 and flip the bits, we get 11110011. And there we have it. In the 1's complement system, the binary representation of -12 is 11110011. This might seem a bit challenging at first, but with practice, you'll find it becomes a natural part of understanding binary number systems. Now, let's delve into a new example to further illustrate how we handle negative numbers in 1's complement representation. Our task here is to convert the decimal number -18 into binary. Similar to the previous example, with negative numbers in the 1's complement system, we initially set aside the negative sign. We only work with the absolute or the magnitude of the number, which in this case is 18. Our first step is to convert 18 into its unsigned binary representation, using 1 byte or 8 bits. In this case, 18 in the unsigned format is 0001010. Now that we have the unsigned binary representation for 18, we're ready to flip the bits, which is the distinguishing step when working with negative numbers in the ones complement system. When we flip the bits of 0001010, every 0 becomes a 1, and every 1 becomes a 0. Hence, our flipped version is 11101101. Therefore, in the ones complement system, the binary representation of -18 is 11101101. This example helps illustrate the steps and reasoning involved in converting negative decimal numbers into ones complement binary representation. In our previous discussions, we learned how to convert decimal numbers into the ones complement, or sometimes referred to casually as ones comp binary representation. Now we're going to reverse the process, converting from ones complement binary back into decimal. The process begins by examining the most significant bit, or MSB, of the binary number. The MSB, usually the leftmost bit, tells us whether the number is positive or negative. Let's take the binary number 0110 as an example. Here, the MSB is 0, indicating that this is a positive number. On the other hand, the binary number 1010 has an MSB of 1, indicating it's a negative number. If the binary number is positive, as indicated by an MSB of 0, we proceed as if it's an unsigned binary number. We simply convert it directly to its decimal representation. However, if the binary number is negative, denoted by an MSB of 1, we need to do a couple of extra steps. First, we flip the bits, swapping the zeros with ones and vice versa. Then, we treat the resulting binary as if it were unsigned, converting it into its decimal equivalent. But don't forget, we need to attach a negative sign to our final answer, since we started with a negative number. Understanding these procedures is crucial when working with one's complement numbers. But as always, the best way to cement this knowledge is through practice. So, next, we'll apply these principles to some concrete examples. Stay tuned as we dive deeper into the fascinating world of one's complement representation. Let's dig into an example of converting a ones complement binary number back into a decimal. Our task here is to convert the binary number 00001011 into a decimal. Firstly, we observe the most significant bit, or the MSB, which is the leftmost bit of our binary number. Here, the MSB is 0. This tells us that the number is positive in one's complement representation. When we are dealing with positive numbers, the process is pretty straightforward. We can treat the binary number as an unsigned binary and convert it directly to its decimal equivalent. To do that, we break down the binary number into the sum of powers of 2. Remember, each bit in the binary number corresponds to a power of 2, starting from 2 raised to the power of 0 at the rightmost bit, and increasing by 1 power for each bit, we move to the left. So, the decimal equivalent of our binary number is 1 from 2 raised to the power of 0, plus 2 from 2 raised to the power of 1, plus 8 from 2 raised to the power of 3. When we add these up, we get 11. Therefore, the ones complement binary number 00001011 converts to the decimal number 11. It's important to remember that when converting from binary to decimal, we don't need to specify the number of bits because they're given in the input. However, when we're converting from decimal to binary, we'll specify the number of bits in the question. This should hopefully clarify the process, and we'll continue practicing with more examples. Let's dive into another example to further consolidate our understanding of converting one's complement binary numbers back into decimal. In this case, we'll deal with a negative number, which requires a couple of additional steps. The binary number we'll convert is 11111011. We start the process by examining the most significant bit, or MSB. The MSB in this case is the leftmost bit, which is 1. This tells us that our binary number represents a negative decimal number. Since our number is negative, we need to perform an additional step before we can convert it to decimal. This step is called flipping the bits. Essentially, we swap each one in our binary number for a 0 and each 0 for a 1. When we flip the bits in our binary number, 11111011, we get 00000100. Once we've flipped the bits, we can then treat our number as if it were an unsigned binary number and convert it to its decimal equivalent. In the binary number 00000100, only the third bit from the right is on. That bit corresponds to 2 raised to the power of 2. All other bits are off, meaning they do not contribute to our decimal number. So our decimal equivalent is simply 4. However, don't forget, we began with a negative binary number. This means that our final decimal number should also be negative. So we attach a negative sign to our decimal number and our final answer is -4. Therefore, the 1's complement binary number 11111011 converts to the decimal number -4. This concludes our examples for this video. However, remember, practice makes perfect. We'll be seeing more examples in another video that will be dedicated solely to exercises. Stay tuned to keep strengthening your understanding of 1's complement representation.